So this video is going to review inverses first, and then we typically talk about inverses in relationship to exponential functions and logarithmic functions, and so that's what's going to happen later on in the video. So first, inverse functions, if you guys recall, inverse operations are operations that undo each other. So, for example, if I had the equation y equals 3x plus 5, the first thing that happened to the x is it was multiplied by 3, and then after it was multiplied by 3, 5 was added to the result. So, if I want to undo everything, then I would take my value at the end and I would subtract 5 first because that's the very last thing that happened. And then I would take that and I would divide it by 3 because that undoes the operation from before that. And so what I would say here is that for the original equation, y equals 3x plus 5, and the resulting equation that undid everything, x minus 5 over 3, that these two are inverse functions. Alright, so there's a couple ways that we end up looking at inverse functions. First is algebraically. So if I want to find an inverse function algebraically, then what I'm going to do is trade the x and y values, and technically once I've traded them, I have found the inverse. However, at that point, instead of having a y equals equation, we would have an x equals equation, and in math we never leave equations like that. And so after we trade the x and y values, we have to solve for y. But technically, the minute we've traded them, we've actually found the inverse. We just have to write it in the proper math notation. So for example, if I had y equals x plus 1 to the third, take away 2, then to find the inverse, I'm first going to rewrite the problem so that the x and y's are traded. Now this is the inverse, but this is not a proper answer, so now I have to undo all the operations and move them over to the other side. So I have x plus 2 equals y plus 1 to the third. And then I need to go from the outside in, so I need to get rid of that third root. And so now I have the third root of x plus 2, and that equals y plus 1. And then I'll go ahead and minus the 1 over. And now we have a special notation to show that the final answer we're getting is an inverse, and you put a little negative 1 as an exponent. And when we read this out loud, we would read this as y inverse is that function. So if the original problem says y equals, then the inverse should say y inverse equals. If the original function said f of x equals, then the inverse function should say f inverse of x equals. So we're just going to make sure that whenever we do an inverse function, we match the notation with the original problem. Alright, now if I was to graph this original problem, and this is not going to be a very exciting example, but I'll show you guys another one. Sorry, I'm changing my graph. I'm just fixing my window. I guess you can watch me while I do it. Okay, so in here I have x plus 1 to the third minus 2, and I'll go ahead and graph that. And now if I look at this original problem, if you can see the domain, it goes left forever and right forever. So for the original problem, I'm going to say that the domain was all real numbers, or you could say negative infinity to positive infinity. And then the range, it goes down forever and it goes up forever. And so the range is also all real numbers. And the reason this is kind of a boring example is because when you go down and you find the domain and the range of the inverse function, then the domain and range from the original just switch places. But in this case, they were the same anyway, so it doesn't really make much difference. But I think I have an example later on where you'll be able to see it more clearly. Okay, so that's if you're doing it algebraically. The next way that we can find inverses is graphically. And so graphically, inverses are symmetric over the line y equals x. And so the way that is the horizontal, or not horizontal, that's the diagonal line that goes this way. So it has a slope of 1 and a y-intercept of 0. So it goes perfectly diagonally through the origin. And they're symmetric over that. And again, you'll just notice, if you look at the graph, that the x and y values have traded. So that is the theme of inverses, is that to undo the operations, really we're just trading x and y. So first we're going to look at a relation. You guys don't typically see these very often, but it's possible. So a relation is just random points that are written like this. There's not necessarily a pattern to them that we could express as an equation. So here, and I'm going to go ahead and say f equals. So here for the relation I would say f inverse, and then all I would do is I would switch the coordinates of the points. And that's it, I've got the inverse. Now for this original problem, for the domain, we would have our x values. X can equal -2, -3, and +3. I was trying to put those in numerical order, but I did it wrong. I guess I could switch that. Sorry, perfectionistic coming out. So we only have those 3 domain values. And then the range here would be y equals 2, 1, and 8. And now if we go down to the inverse relation, then we would say the domain is x equals 1, 2, and 8. And the range is that y equals -3, -2, and 3. So you can kind of see how that works. The domain and the range trade as well. So if anyone ever asks you, and this is a common standardized testing question, find the domain of the inverse function, well then look at the range of the original function, and that's just what the answer is. So that's pretty cool. Alright, so next, actually we're going to do this on graph paper. Next, to check graphically, we're going to go ahead and find the inverse of the function y equals x squared plus 3. So I'm going to start off by graphing the original function. And I have this memorized, which is how I'm doing this so quickly. But if you needed to graph the original function, you could certainly do that on your calculator. So this is a parabola that's been shifted up 3. And then what I would do, if all I had was the graph, is I would pick some points that are on the graph, and then I would just trade the values for those. So this is -2, 7. No, -2, 8. No. 1, 2, 3, 4, 5, 6, 7. -2, 7. And then we have -1, 4. And we have 0, 3, and 1, 4. And 2, 7. So those are all the points that I had drawn to begin with. So that is the original. And then if I wanted to know what the inverse was so that I could graph it, I would just switch the x and the y coordinate for all of these, and then I would be able to graph it. So I have 1, 2, 3, 4, 5, 6, 7, -2. And 4, -1, and 3, 0, and 4, +1, and 7, +2. And then if you want to make sure that it's symmetric over the line y equals x, that's right here. So if you can picture folding your paper in half across that line, then it would definitely be symmetric over that line. So now, and if I wanted to write this equation, I could just say this is x equals y squared plus 3, right? I just traded the x and the y. And then I could solve for y to figure out this equation, so I could minus 3 from each side. X minus 3 equals y squared, and then I would square root. And in this case, we have to be really careful to write plus or minus x minus 3 equals y. And you will notice that since I traded this graph, this inverse is definitely not a function, right? It does not pass the vertical line test. So we would say the original graph was a function, the inverse was not, all right? So it's an inverse equation, but definitely not a function. Okay, so if we look at the original had a domain of negative infinity to positive infinity, and went left forever and right forever. But the range, at the very lowest, it was positive 3, and then it went up forever. And if we look over here, they're exactly the opposite. So the domain starts at 3 and goes right forever, and the range is down forever and up forever. Okay, next we're going to look at how to check for inverses. So the way that we check inverses is through composition of functions. And if you guys remember, the composition of functions would be taking one function and putting it inside of another one. So if we had the original function was f of x, and the inverse function was f inverse of x, then we should say that the original function, if I plug the inverse into it, like this, the original function and the inverse function would cancel out, and the result would just be x. Or we could say I'm going to start with the inverse as the outside function, and then I'm going to plug the original function inside, and again, these two things should cancel, and they should simplify to x. And it doesn't matter which way you go. Some math classes would have you do it each way to prove that they both simplify to x, but in reality, if one of them does, then the other one is going to as well. So let's look at the original example we had. If we have y equals 3x plus 5, and if we have y equals x minus 5 over 3, let's say I want to use this one as the outside function. So I have 3 times whatever I'm going to plug in for x plus 5. And then if I go ahead and take this one and plug it inside, that gives me x minus 5 over 3. And then if I simplify this, you'll notice that the multiply by 3 and the divide by 3 cancel first. And then I have x minus 5 and plus 5, and I don't need those parentheses anymore. And then the minus 5's cancel, and I'm left with just x. And I could also do it the other way. I could also do it starting with this one. Oops, I should not write the x. So I'm going to say I'm going to plug something in for x, and then I'm going to take away 5 from it, and then I will take that whole thing and divide it by 3. And if I go back and I plug this one in, 3x plus 5, technically I don't really need those parentheses there, so I can kind of ignore them. The plus 5 and the minus 5 cancel out, and then I'm left with 3x over 3. And the 3's cancel out, and that just simplifies to x. So again, it works with that problem. Okay, and then now we're going to move on to exponential graphs and logarithmic graphs. And this is going to be pretty brief because you have learned it before. We are just reviewing. Alright, so exponential graphs, the parent graph would be y equals b to the x. You'll notice that the variable is actually as the exponent. B stands for base. So you could have like y equals 2 to the x, or y equals 3 to the x, or y equals 1/2 to the x. There are lots of options for what the base could be, and all of those are going to look a little bit different. So as far as the transformations go, we can still have the same transformations we've talked about in the past. And I guess actually I could add in, I don't know what letter, will you see? That's the letter right here. Okay. So the A, if I have the absolute value of A is greater, we're talking about a vertical stretch, like normal. If I'm talking about the absolute value of A is less than 1, then that's a vertical compression. If the A value is negative, then we're talking about reflecting over X. All right. B again is the base, and so that is not a transformation. It just tells you which parent function specifically you're going to use. Again, we can talk about our new transformation with the C. So if the absolute value of C is greater than 1, it's the opposite of what you would think, where it's a horizontal compression. If the absolute value of C is less than 1, then it's a horizontal stretch. And if you have C is a negative, then it's a reflection over Y, the Y-axis. Here we have left and right. If it's a plus, it goes to the left. If it's a negative, it goes to the right. And on the end, we've got up and down. Down if it's negative, up if it's positive. All right, now the important thing to notice is that on these graphs, we actually end up having horizontal asymptotes. We have Y values that we cannot equal. And those horizontal asymptotes, we have this part right here can kind of zero out. It can get really, really close to 0, not quite there. But the K value, we're never going to be able to have that value exactly, because since this doesn't go to 0 exactly, it can just get really close to it. That K value is never going to be all by itself. And the reason we can't get exactly to 0 over here is because anytime you take a base and raise it to an exponent, there's no way to raise a base to an exponent and get a 0. Even if you did b to the 0, that would still be 1. So we can get these numbers to be super, 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 super tiny. We can try to zero it out, but we're never actually going to reach it there. And so these always have horizontal asymptotes at y equals k. Whatever that number is on the end is a horizontal asymptote. So if we have the equation y equals negative 2 times 3 to the x plus 1 minus 4, then I'll go ahead and graph this on my calculator. Times 3 to the x plus 1 minus 4. And if you look at that, you can see this graph has been reflected over the x-axis. And maybe I'm going to actually go ahead and graph the original so you can compare 3 to the x. Okay. So there's the original. So it's been reflected over the x-axis. It's going down now. It's stretched by 2 vertically, which we can't really see because it's been moved. You know, you can't see much on the graph anyway. But you can see it has been shifted left a little bit. And you can see originally this would have a horizontal asymptote at 0, and it's moved down 4. And so that horizontal asymptote is now at negative 4. And so we're seeing all those pieces there. So we would say this has a horizontal asymptote of y equals negative 4. Okay. Next, if we look at logarithmic functions, this would be y equals log base b of x. And again, base b could be anything. So we could say y equals log base 2 of x, or we could say y equals log of x. If you guys recall, this is the common logarithm, and if it doesn't have a base written, the base is really 10. So again, if we have this written with the transformations, I'm going to show you what that form looks like. But I'm not going to write the transformations out again because you know what they are. So we can have the number in the front, and then we have our horizontal part in front of our parentheses, and then the k at the end. And this time we have x equals h is the vertical asymptote. All right. So this part in here, you cannot make this part in here equal 0. That's a value you can't get to. There's always going to be something there. And so that's a vertical asymptote because you can't actually plug in. You couldn't have like x minus 5 and then put a 5 in there because you can't have 0 there. All right, so for example, if we have y equals 1/2 log base 2 of x plus 3 minus 1, this one, just looking at it, I can see that it has a vertical asymptote of negative 3. X equals negative 3 is what we can't have there. And now this one is good to talk about because these are hard to plug in on your calculator if you have an old calculator. So go ahead and hit y equals, and then we're going to check to see if we have the log button. If you have a new calculator, you're going to hit the math button, and if you go up, you're going to see option A, which says log base, and it looks like that, and I guess I should have plugged my 1/2 in before. So I'm going to go to the L, and I'm going to hit insert, I-N-S, insert, 1 divided by 2, like that. My base is 2, and then I have x plus 3 and minus 1. Now, if you have an older calculator, you're going to have to know how to plug this in like the old school way. So you guys are going to plug it in as y equals 1/2 log of x plus 3 divided by log of 2, like that. That's how you plug in this part that's kind of messy, and we're going to have parentheses around this, and then you're going to minus 1. So that's the way you're going to write yours. So 1 divided by 2 log, and that's just hitting the actual log button down here if you have an older calculator. X plus 3, oops, only 1, divided by log of 2 minus 1. And if we graph these, hopefully I plugged it in right, and you can see that it ends up being the same. Yes, perfect. Okay. So this graph has been compressed horizontally. It has shifted left 3 and down 1, and you can see we have a vertical. It appears that it completely stopped, but it did not. It just, your graph is going to have a hard time graphing that. So it has a vertical asymptote of negative 3.